You're standing on a planet hurtling through space at 67,000 miles per hour. Right now, something else is racing toward you even faster, something that travelled for millions of years across the frozen void between stars, something that doesn't belong to our solar system. 3I/Atlas, an interstellar object, and it's making its closest approach to Earth in exactly 23 days. Your social media feeds are exploding with panic. Doomsday predictors claim it'll trigger catastrophic earthquakes. Conspiracy theorists whisper about government cover-ups. But you want the truth, not the hysteria. You want to know what NASA knows, what the math actually says, why every space agency on Earth is watching this visitor with fascination instead of fear. Because here's what makes this moment remarkable: you have access to the same data scientists use. You can understand the orbital mechanics. You can see why Earth is safe. And why that answer is more mind-blowing than any disaster scenario. If that sounds like your kind of content, if you value science over sensationalism, go ahead and like this video. Subscribe if you want more cosmic truth-telling. And hit that bell when you're genuinely excited to join us for the next discovery. Let's meet our interstellar visitor. On October 13th, 2024, astronomer Robert Weryk was doing what he does every clear night at the Atlas Observatory in Hawaii, scanning the sky for anything that moves. His twin telescopes sweep across millions of stars, hunting for asteroids that might pose a threat to Earth. But at 3:47 a.m. local time, something appeared on his screen that made him stop cold. A faint dot of light, moving fast, too fast. Weryk ran the calculations 3 times because the numbers didn't make sense. This object was travelling at 87 miles per second relative to the Sun. That's over 313,000 miles per hour. For context, the fastest human-made object, the Parker Solar Probe, tops out at 430,000 miles per hour, and it required a massive rocket and multiple gravity assists to reach that speed. This thing was naturally moving at 2/3 that velocity. But speed alone wasn't the giveaway. What caught Weryk's attention was the trajectory. Every asteroid, every comet, every piece of space debris in our solar system follows a predictable pattern. They orbit the Sun in ellipses or parabolas, bound by gravity like planets on invisible tracks. This object's path was hyperbolic, a mathematical term that means one simple thing: it's not coming back. It arrived from interstellar space, and it's leaving to interstellar space within 48 hours. Observatories on 3 continents confirmed what Weryk suspected. The European Space Agency's tracking station in Spain locked onto it. NASA's JPL in California calculated its orbit. The object received its official designation 3I/Atlas. The 3I stands for Third Interstellar Object. The first was Oumuamua in 2017, the second was Comet Borisov in 2019. And now, 5 years later, we had another visitor from beyond. You might be wondering, how do we know for certain it's interstellar? The answer lies in orbital energy. Every object bound to our Sun has negative orbital energy, meaning gravity keeps it trapped in our solar system, but 3I/Atlas has positive orbital energy. Dr. David Farnokia from NASA's Center for Near-Earth Object Studies explained it perfectly. It's like throwing a ball upward. If you don't throw it fast enough, it falls back down. But throw it past escape velocity, and it never returns. 3I/Atlas is that ball, except it was thrown by another star system billions of miles away. The initial observations revealed something fascinating about its composition. Unlike Oumuamua, which was rocky and cigar-shaped, and unlike Borisov, which was an active comet spewing gas and dust, 3I/Atlas appears to be something in between. Spectroscopic analysis. The technique where astronomers split light into its component colours to identify chemical signatures showed traces of water ice, organic compounds, and silicate minerals. It's a cosmic hybrid, carrying materials from wherever it was born. And where was it born? That's the million-dollar question. Astronomers traced its trajectory backward through space, rewinding its journey like a cosmic video. The calculations suggest 3I/Atlas has been travelling for approximately 40 million years. Let that sink in. When this object began its journey, Earth was in the Oligocene epoch. Early primates were just starting to evolve. Saber-toothed cats roamed the continents, and somewhere out there, perhaps around a star we can't even identify with our telescopes, something ejected this object into the void. Dr. Michelle Bannister, a planetary astronomer at the University of Canterbury, described interstellar objects as messages in bottles from other solar systems. She's right. Every interstellar visitor carries information about stellar neighbourhoods we may never visit. The ratio of rock to ice tells us about formation temperatures. The organic molecules hint at chemical processes happening around distant stars. The trajectory reveals gravitational interactions with planets we'll never see. But here's what makes 3I/Atlas unique among its interstellar cousins' timing and accessibility. Oumuamua was discovered when it was already leaving our solar system. We barely had time to point our telescopes at it before it vanished. Borisov gave us more time, but it stayed far from Earth, never closer than 190 million miles. 3I/Atlas, however, is different. Its trajectory brings it within 26 million miles of Earth on March 14th, 2025. 26 million miles might sound like a vast distance. And it is. You're absolutely right to think so. That's about 108 times the distance from Earth to the Moon. But in astronomical terms, that's practically a close encounter. It's close enough that even amateur astronomers with decent backyard telescopes will be able to spot it. Close enough that every major observatory on Earth will have it in their sights for weeks. Close enough that some people started to panic. Because here's the thing about human psychology, we're terrible at processing cosmic distances. Our brains evolved to understand the distance from our cave to the watering hole, not the distance between planets. When people hear closest approach, they imagine something bearing down on us like a freight train. News headlines didn't help. Interstellar object on collision course with Earth, one tabloid screamed. Mystery visitor sparks concern among scientists, another claimed. But Robert Werrick, the astronomer who discovered it, had the perfect response when asked if he was worried. He laughed and said, "I'm more concerned about the drive home from the observatory. The odds of a car accident are infinitely higher than 3I/Atlas hitting Earth." He's not being flippant, he's being mathematically accurate. So why the certainty? How can astronomers be so confident that this cosmic bullet, travelling faster than anything we've ever built, poses zero threat to our planet? The answer lies in something beautifully simple mathematics, not complicated equations that require a PhD to understand, but fundamental geometry and physics that you could calculate on a napkin. And understanding those calculations reveals not just why we're safe, but how we know, with absolute precision, where 3I/Atlas will be at every moment of its journey through our neighbourhood. Let's break down the numbers that guarantee our safety. Imagine you're standing on a train platform. A bullet train approaches at 200 miles per hour, but it's on a parallel track 100 feet away. You feel the wind, you hear the roar, but you're never in danger. That's essentially what's happening with 3I/Atlas, except the speeds are exponentially higher and the parallel track is carved by gravity itself. The first thing that makes 3I/Atlas remarkable is its eccentricity. In orbital mechanics, eccentricity measures how stretched out an orbit is. A perfect circle has an eccentricity of 0. Earth's orbit around the Sun has an eccentricity of 0.017, nearly circular. Halley's Comet, which loops back every 76 years, has an eccentricity of 0.967, but 3I/Atlas, its eccentricity is 1.73. Wait, how can something have an eccentricity greater than 1? Doesn't that break the math? Not at all. It means the orbit isn't an ellipse. It's a hyperbola. Picture it this way. Elliptical orbits are closed loops, like a racetrack. Hyperbolic trajectories are open curves, like a highway off-ramp. 3I/Atlas entered our solar system on one side of the Sun, curved around due to gravity, and it's exiting on the other side. One-time visitor, no return ticket. Dr. Paul Chodas, Director of NASA's Center for Near-Earth Object Studies. Put it plainly, objects with eccentricity greater than 1 are not gravitationally bound to the Sun. They're just passing through, like a tourist taking a shortcut through our cosmic neighborhood. And that hyperbolic path is precisely why we can predict its location with such extraordinary accuracy. Here's where the numbers get beautiful. Astronomers tracked 3I/Atlas across 47 nights of observations from October through December 2024. They measured its position against background stars, calculated its velocity vector, and fed all that data into orbital determination software. The result, they know its trajectory to within a margin of error of just 3,000 miles. That sounds like a lot, but remember, we're talking about an object that's travelled trillions of miles. A 3,000 mile uncertainty over that distance is like measuring the length of a football field to within the thickness of a human hair. On March 14th, 2025, at precisely 11:23 p.m. Universal Time, 3I/Atlas will reach its point of closest approach to Earth, the distance 26.4 million miles, or 0.284 astronomical units if you want the technical term. To put that in perspective, Venus, our closest planetary neighbour, comes within 25 million miles during its nearest approaches, and we don't panic about Venus. Mars at its closest gets within 35 million miles. 3I/Atlas will pass between those two distances. But here's the critical detail, it's not just about distance, it's about the geometry of the encounter. Imagine you're watching two airplanes from the ground. They might appear to be on a collision course from your vantage point, but one is at 30,000 feet and the other is at 35,000 feet. They're in completely different altitudes. 3I/Atlas and Earth are in different orbital planes. Earth orbits the Sun in a relatively flat plane called the ecliptic. Most planets, asteroids, and comets orbit within a few degrees of this plane, but 3I/Atlas is tilted at an inclination of 42 degrees relative to the ecliptic. Picture a dinner plate representing Earth's orbit. Now take a second plate and tilt it at a steep angle so it intersects the first plate. 3I/Atlas is on the tilted plate. The two paths cross at specific points, but 3I/Atlas and Earth are never at those crossing points at the same time. Dr. Marina Brozovic from JPL's radar astronomy team explained it with a perfect analogy. It's like two cars approaching an intersection. One car arrives at 3:00 p.m, the other at 9:00 p.m. They use the same intersection, but they're never there simultaneously. 3I/Atlas and Earth share spatial coordinates in three-dimensional space, but they're separated by time. The speed difference reinforces our safety. Earth orbits the Sun at 67,000 miles per hour. That's our cruising speed. Constant and predictable. 3I/Atlas, however, is moving at 87 miles per second. That's 313,200 miles per hour, nearly 5 times faster than Earth. When you're moving that much faster than something else, even if your paths theoretically intersect, you blast through the intersection long before the other object arrives. Think of it like this. If Earth is a jogger and 3I/Atlas is a Formula One race car, Even if they're both heading for the same spot, the race car will scream past and be miles down the road before the jogger even gets close. The temporal separation is absolute. But let's address the elephant in the room. What if the calculations are wrong? What if there's some unknown factor that could alter 3 I/Atlas's path at the last moment? This is where things get interesting, because it reveals a fundamental difference between science fiction and science fact. In movies, asteroids suddenly veer off course, gravity wells appear out of nowhere, orbits change unpredictably. But in reality, space is governed by laws so precise that we can calculate planetary positions thousands of years into the future. Isaac Newton figured out the basic equations in 1687. We've refined them with Einstein's general relativity. But the fundamentals remain rock solid. For 3 I/Atlas to deviate from its predicted path, something would need to exert force on it. Gravity from an unseen planet would detect that planet's gravitational influence on other objects, outgassing from the object itself. Like a comet's jets, astronomers are monitoring for exactly that. And 3 I/Atlas shows minimal activity, a collision with another object. The odds of that happening in the vastness of space, especially in the few weeks before closest approach, are so infinitesimally small that you're literally more likely to win the lottery 5 times in a row. The European Space Agency's Near-Earth Object Coordination Centre ran Monte Carlo simulations, computational models that factor in every possible uncertainty. They ran the encounter 10,000 times, with slightly different initial conditions, in every single simulation. 3 I/Atlas passed Earth harmlessly, the closest approach in the worst-case scenario, still 25.1 million miles away, comfortably safe. So when you see the headlines, when your uncle shares that alarming Facebook post, remember this: the same mathematics that lets us land rovers on Mars with pinpoint accuracy, the same physics that predicted the 2017 solar eclipse to the exact second. Those same principles guarantee that 3 I/Atlas poses zero threat, but understanding why we're safe is only half the story. Because while this visitor won't harm us, there are objects out there that could. And knowing the difference between a harmless passerby and a genuine threat reveals just how sophisticated our planetary defense systems have become. Let's talk about what actually keeps astronomers awake at night, because it's not 3 I/Atlas. It's the 30,000 near-Earth asteroids we've discovered so far, and the estimated 15,000 more we haven't found yet that are large enough to cause regional devastation. February 15th, 2013. Chelyabinsk, Russia. You're driving to work on a cold winter morning when the sky suddenly lights up brighter than the sun. A fireball streaks overhead, leaving a trail of smoke 20 miles long. Then, the shockwave hits. Windows shatter across 6 cities. Over 1,600 people are injured, mostly from flying glass. The explosion releases energy equivalent to 500 kilotons of TNT, roughly 30 times the Hiroshima bomb. Here's the terrifying part: nobody saw it coming. The Chelyabinsk meteor was only 66 feet across, smaller than a suburban house. It approached from the direction of the sun, which meant telescopes couldn't spot it against the glare. Total warning time 0. The object exploded 18 miles above the ground, and if it had been just slightly larger, or if its angle of entry had been steeper, the ground-level destruction would have been catastrophic. Dr. Peter Brown from the University of Western Ontario analysed the event and concluded, Chelyabinsk was a wake-up call. It demonstrated that even relatively small objects can cause significant damage, and our detection systems had a massive blind spot. That blind spot has since been addressed. But the event proved something crucial: the universe doesn't announce its arrivals. Now scale up. In 1908, another object exploded over Siberia near the Tunguska River. This one was estimated at 120 feet across. It detonated with the force of 15 megatons, flattening 770 square miles of forest. That's an area larger than New York City. 80 million trees were knocked down in a radial pattern. If this had happened over a populated area, the death toll would have been in the millions. What if it had been even bigger? Let's talk about Apophis, an asteroid that sent ripples of concern through the scientific community when it was discovered in 2004. Apophis is roughly 100 feet across, about the size of 3 football fields. Initial calculations showed it had a 2.7% chance of impacting Earth on April 13th. 2029. 2.7% might not sound like much, but in asteroid terms, that's terrifyingly high. Can you imagine the global response if there was even a 1 in 37 chance of a football field-sized asteroid hitting Earth? Financial markets would crash. Governments would activate emergency protocols. The psychological impact alone would be staggering. Fortunately, additional observations refined Apophis's orbit. We now know with certainty that it will pass Earth safely in 2029, coming within 19,000 miles. Actually closer than some of our satellites. But here's the critical difference between Apophis and 3I/Atlas. Apophis is gravitationally bound to the Sun. It orbits in our neighbourhood. It comes back every few years, giving us multiple opportunities to track it, study it, and refine our predictions. Apophis represents a known threat that became a known non-threat through diligent observation. That's the system working correctly. But what keeps planetary defense experts up at night are the unknown unknowns. The asteroids we haven't discovered yet that could be on collision courses we haven't calculated. According to NASA's estimates, we found approximately 95% of near-Earth asteroids larger than 3,000 feet across. That's the good news. These are the civilization enders, the Chicxulub-sized impactors that caused the dinosaur extinction 66 million years ago. We're pretty confident we've spotted most of them, and none pose a threat for at least the next century. But drop down to the 500-foot size range, objects large enough to devastate entire countries, and we've only found about 40% of them in the 150-foot range, the Tunguska-class impactors. We've discovered less than 10%. There are tens of thousands of these objects out there, silent and invisible, following their orbital paths with no regard for whether Earth happens to be in the way. Dr. Amy Mainzer, principal investigator for NASA's Near-Earth Object Wide Field Infrared Survey Explorer, explained the challenge perfectly. Finding asteroids is like looking for a lump of coal in the night sky. They don't emit light, they're dark, they're small, and space is incomprehensibly vast. The only reason we see them at all is because they reflect a tiny bit of sunlight. This is why 3I/Atlas, despite its interstellar origin and dramatic speed, doesn't rank on the threat assessment scale. We know exactly where it is. We know precisely where it's going. Its hyperbolic trajectory means it's passing through once and never returning. There are no orbital uncertainties, no gravitational perturbations from Jupiter that could nudge it onto a different path. No future close approaches to recalculate. The real danger comes from objects with orbital periods that bring them back repeatedly, each time with slightly different geometries due to gravitational interactions with planets. These are the asteroids that require constant monitoring, continuous refinement of orbital projections, and long-term threat assessments. Take asteroid Bennu, for example. NASA spent 2 years studying it up close with the OSIRIS-REx mission, even collecting samples from its surface. Why dedicate an entire spacecraft to one asteroid? Because Bennu has a 1 in 2,700 chance of impacting Earth between 2175 and 2199. That might sound like low odds, but it's high enough to warrant serious attention. By studying Bennu's exact mass, composition, rotation, and surface properties, scientists can refine impact predictions and, if necessary, design deflection missions with surgical precision. This brings us to a fundamental truth about planetary defense. It's not about preventing every possible impact. It's about early detection, accurate tracking, and having enough lead time to do something about it. An asteroid detected 50 years before potential impact gives us options. One detected 50 days before impact gives us prayers. The Chelyabinsk meteor, 0 warning. The Tunguska event, 0 warning. These weren't failures of technology, they were limitations of the technology available at the time. But we've learned, we've adapted, we've built systems specifically designed to find these threats before they find us. So while 3I/Atlas makes headlines because of its exotic origin, the real story of planetary safety is being written by the astronomers who spend every clear night scanning the sky, cataloguing objects, calculating orbits, and building the database that keeps our planet secure. And that scanning network is far more sophisticated than most people realize. Picture a global surveillance network that never sleeps, never blinks, and watches over 100 million cubic miles of space every single night. That's not science fiction. That's the planetary defense system protecting you right now. The Atlas system, the very network that discovered 3I/Atlas, operates 4 telescopes spread across 2 hemispheres, 2 in Hawaii, 1 in Chile, 1 in South Africa, every night. These robotic telescopes scan the entire visible sky twice. They take images every 60 seconds, comparing each new image against the previous one to detect anything that moves. It's like having 4 security cameras watching every corner of a warehouse. Except the warehouse is the entire sky, and the intruders are cosmic projectiles travelling at tens of thousands of miles per hour. How sensitive are these telescopes? They can detect an object the size of a small car at a distance of 1 million miles. That's roughly 4 times the distance to the moon. Dr. Larry Deno, a principal investigator for Atlas, described the system's capability this way. If someone turned on a flashlight on the moon, Atlas would see it. We're not just looking for big, obvious threats. We're looking for anything that moves, anything that changes, anything that doesn't belong. But Atlas isn't working alone. The Catalina Sky Survey in Arizona has been hunting near-Earth objects since 1998, discovering over 8000 asteroids, including more than 900 potentially hazardous ones. Their telescope sweeps the sky methodically, covering an area 40 times larger than the full moon in each image. On a good night, they process over 10 terabytes of data. That's equivalent to recording 2000 hours of high-definition video every single night. Then there's PAN-STARRS, the Panoramic Survey Telescope and Rapid Response System in Hawaii. Its 1.8-meter telescope uses a camera with 1.4 billion pixels, one of the largest digital cameras ever built. To put that in perspective, your smartphone camera is maybe 12 to 48 megapixels. PAN-STARRS is capturing images at nearly 30,000 times that resolution. Every 3 days, it images the entire visible sky, creating a constantly updating map of anything that moves. Do you realize what this means at any given moment? There are professional astronomers and automated systems scanning the heavens specifically to find objects before they become threats. Not because there's an immediate danger, but because the best defense is measured in decades, not days. The European Space Agency contributes through their Space Situational Awareness Program, operating telescopes in Spain and Italy. They focus on objects making close approaches to Earth, refining orbital calculations to eliminate false alarms and identify genuine concerns. In 2023 alone, the network tracked over 1,200 close approaches, calculated precise trajectories for each one, and issued exactly 0 warnings because every single object passed harmlessly. But ground-based telescopes have limitations. They can't observe during daylight. Clouds block their view. And as we learned from Chelyabinsk, objects approaching from the sun's direction are nearly impossible to spot from Earth's surface. That's why NASA is developing the NEO Surveyor, an infrared space telescope specifically designed to find asteroids. Infrared is the game changer here. Invisible light. Asteroids are dark and hard to see, but in infrared, they glow because they absorb sunlight and re-emit it as heat. NEO Surveyor will orbit the Sun between Earth and Venus, giving it a vantage point where it can see asteroids silhouetted against the cold background of space, even if they are approaching from the Sun's direction. Launch is scheduled for 2027 and within 5 years of operation. NASA expects it to discover over 200,000 near-Earth objects. Think about that timeline. Right now, we know of about 30,000 near-Earth asteroids. In the next decade, we'll likely catalogue 7 times that many. Our knowledge of what's out there is about to explode. But discovery is only step 1. Once you find an object, you need to track it obsessively. This is where the International Astronomical Union's Minor Planet Center comes in, located at the Smithsonian Astrophysical Observatory in Cambridge, Massachusetts. It serves as the global clearinghouse for asteroid observations. Every telescope that spots an asteroid reports its position to the Minor Planet Center. They collect data from over 200 observatories worldwide, processing more than 3 million observations per year. Dr. Matthew Holman, director of the Minor Planet Center, explained their role. We're like air traffic control for space rocks. Astronomers send us positions, we compute orbits, and we alert the world if something needs attention. The system works because it's collaborative. No single telescope can watch the whole sky, but collectively, we miss very little. When a new object is detected, the Minor Planet Center issues an alert within hours. Observatories around the world then target that object to gather more data. With each observation, the orbital uncertainty shrinks. After a few days of tracking, astronomers can predict where an object will be months in advance. After a few weeks, they can project its path for decades. After a few months of data, orbital predictions become accurate for centuries. This is precisely what happened with 3I/Atlas. Initial observations gave a rough trajectory. Follow-up observations from Chile, South Africa, Australia, and Europe refined it. Within 30 days, astronomers had enough data to calculate its closest approach to Earth with pinpoint accuracy. Not just for 2025, but for its entire journey through our solar system. The network even has backup systems. NASA's Scout system automatically evaluates newly discovered objects, calculating impact probabilities within minutes of detection. If Scout flags something concerning, it triggers alerts to the NASA's Planetary Defense Coordination Office, which coordinates observations from military and civilian telescopes worldwide to gather urgent follow-up data. And here's something most people don't know you can help. The International Astronomical Union operates a platform called Asteroid Citizen Science, where amateur astronomers contribute observations. In 2022, amateur astronomers provided nearly 400,000 observations that helped refine asteroid orbits. Your backyard telescope might spot something professionals missed. But what happens when all this surveillance, all this computing power, all this international cooperation identifies a genuine threat? What if the calculations show an asteroid is actually going to hit Earth? That's when planetary defense shifts from detection to action, and the options available might surprise you. September 26th, 2022, a NASA spacecraft the size of a golf cart travelling at 14,000 miles per hour slammed into an asteroid 7 million miles from Earth. The impact was deliberate. The mission was called DART, the Double Asteroid Redirection Test, and it proved something extraordinary: humanity can move asteroids. The target was Dimorphos, a moon orbiting a larger asteroid named Didymos. Dimorphos is roughly 530 feet across, about the size of the Great Pyramid of Giza. Before impact, it orbited Didymos once every 11 hours and 55 minutes. DART's collision, moving at 6 kilometers per second, transferred momentum to the asteroid moon like a cosmic billiard ball. What happened next exceeded every prediction. Scientists expected to change Dimorphos's orbital period by about 7 minutes. The actual result, the orbit shortened by 33 minutes, nearly 5 times more effective than anticipated. Dr. Nancy Chabot, DART coordination lead at Johns Hopkins Applied Physics Laboratory, couldn't hide her excitement. We moved an asteroid, we changed its motion in a measurable, predictable way. This wasn't theoretical, this was real. But why did it work so much better than expected? The impact created a massive plume of debris, rocks and dust blasting off the surface at high speed. That ejector acted like a rocket thruster, pushing the asteroid even further than the spacecraft's impact alone could achieve. It's called momentum enhancement, and the factor measured at approximately 3.6, meaning the total momentum change was 3. 6 times greater than the impacting spacecraft's momentum alone. Think about what this means. You don't need a nuclear weapon. You don't need to land on an asteroid and drill into it like in the movies. You just need to hit it hard enough, early enough, and physics does the rest. A small change in velocity, just a few millimeters per second, compounds over years into a massive change in position. Given 10 years of warning, a DART-style impact could shift an asteroid's path by thousands of miles, turning a direct hit into a clean miss. The European Space Agency is already building the follow-up mission. Hera will arrive at Dimorphos in 2026 to study the crater, measure the asteroid's internal structure, and gather data that will inform future deflection missions. They're treating DART not as a one-time experiment, but as the first chapter in an operational planetary defense capability. But kinetic impactors like DART only work if you have years or decades of warning. What if we detect an asteroid on a collision course with only months to spare? Then the options get significantly more complicated and dramatically more powerful. This is where nuclear deflection enters the conversation. And no, it's not about blowing up the asteroid. Hollywood got that completely wrong. Exploding an asteroid into fragments doesn't solve the problem, it multiplies it. Instead of one large impact, you get hundreds of smaller impacts spread across a wider area. You've turned a rifle bullet into the shotgun blast. The actual strategy is called a nuclear standoff burst. You detonate a nuclear device near the asteroid, not on it. The explosion vaporizes a layer of the asteroid's surface, and that vaporized material blasts away from the asteroid at tremendous speed, creating thrust. It's like a momentary rocket engine powered by nuclear energy. The asteroid gets pushed in the opposite direction of the vaporized plume. Scientists at Lawrence Livermore National Laboratory have run simulations on this exact scenario. A 1 megaton nuclear device detonated 300 feet from a 1000-foot asteroid could change its velocity by several centimeters per second. That doesn't sound like much, but remember, in space, even tiny changes accumulate. A deflection applied 6 months before impact could shift the asteroid's trajectory by thousands of miles. Dr. Brent Barbee, an aerospace engineer at NASA's Goddard Space Flight Center, explained the appeal. Nuclear standoff deflection gives us an option when kinetic impactors aren't enough. If we find a large asteroid with only short warning time, nuclear might be our only practical solution. The technology exists. The delivery systems exist. What we need is political and international coordination. And that coordination is already happening. The United Nations established the International Asteroid Warning Network and the Space Mission Planning Advisory Group specifically to coordinate global responses to asteroid threats. 18 space agencies, including NASA, ESA, Russia's Roscosmos, and China's CNSA, participate. They run annual exercises simulating asteroid impact scenarios, testing communication protocols and decision-making frameworks. In 2021, they simulated a scenario where a 1,300-foot asteroid was discovered 6 months before impact. The exercise revealed critical gaps in international coordination, uncertainty in decision timelines, and the political complexity of deploying nuclear devices in space. But it also demonstrated that the infrastructure for cooperation exists. The conversations are happening at the highest levels of government. Beyond kinetic impactors and nuclear options, scientists are exploring gravity tractors. The concept sounds like science fiction but is grounded in solid physics. You park a spacecraft near an asteroid, not landing on it, just hovering nearby. The spacecraft's tiny gravitational pull tugs on the asteroid. Over months or years, that gentle, constant pull shifts the asteroid's orbit. The advantage is completely controlled. You can apply thrust precisely, adjusting in real time based on observations. The disadvantage, it's slow. Gravity tractors only work with decades of warning, but for long-term threats, they offer surgical precision without explosive risks. ESA studied this concept in detail with their proposed Don Quixote mission. Though it hasn't flown yet due to budget constraints, the mission would send 2 spacecraft to an asteroid, Hidalgo would impact it, and Sancho would observe the results while also testing gravity tractor techniques. The engineering is proven, the physics is understood. It's just waiting for the political will and funding. Then there's the ion beam shepherd, a variation where instead of using gravity, you blast the asteroid with a stream of ions from a spacecraft thruster. The ions transfer momentum gradually, pushing the asteroid like wind filling a sail. Japan's Hayabusa 2 mission demonstrated ion propulsion technology, keeping a spacecraft stationed at an asteroid for over a year. Scaling this up for deflection purposes is theoretically straightforward. What all these methods share is a common requirement time. The earlier you detect a threat, the more options you have and the less force required. An asteroid detected 50 years out could be deflected with a spacecraft weighing just a few tons. The same asteroid detected 2 years out might require nuclear intervention. Detected 6 months out, you're looking at evacuation plans, not deflection missions. This is why the survey networks, the tracking systems, the international coordination, all of it exists. Because planetary defense isn't about responding to emergencies. It's about ensuring emergencies never happen in the first place. And when it comes to 3I/8LAS, all of this infrastructure, all of this preparation, confirms what the math already told us: we don't need any of it. No deflection required, no international emergency protocols necessary, just observation, calculation, and confidence. But that confidence comes from something else equally valuable, the knowledge we're gaining from watching this visitor up close. Imagine receiving a postcard from another solar system. That's essentially what 3I/8LAS represents, a physical sample of matter that formed around a different star, travelled across the interstellar void, and arrived in our cosmic neighbourhood carrying information we can't obtain any other way. When Oumuamua blazed through in 2017, astronomers were caught off guard. It was already leaving the solar system when we discovered it, racing away at 58,000 miles per hour. We managed to observe it for only 11 days before it became too faint for even our most powerful telescopes. In that brief window, we learned it was elongated, tumbling end over end, and accelerating slightly in ways that couldn't be explained by gravity alone. That acceleration sparked endless debates. Was it outgassing like a comet? Was it a light sail pushed by solar radiation? The mystery remains unsolved because we simply ran out of time. Comet Borisov in 2019 gave us a longer observation window, about 3 months of quality data. Spectroscopic analysis revealed it contained water, carbon monoxide, and complex organic molecules. Its composition closely matched comets from our own solar system, suggesting that comet formation processes might be universal. Dr. Stefano Bagnulo from the Armagh Observatory captured the significance perfectly. Borisov told us that what happens here happens elsewhere. The chemistry of planet formation isn't unique to our Sun, but 3I/Atlas offers something neither of its predecessors could: optimal geometry and extended visibility. Its trajectory brings it close enough for detailed observation while moving slowly enough, relatively speaking, that we'll be able to track it for nearly 6 months. From December 2024 through May 2025, this object will be visible to professional observatories, giving scientists an unprecedented opportunity to study an interstellar visitor. What are they looking for? Start with composition. Every element absorbs and emits light at specific wavelengths, creating a unique fingerprint. When astronomers split the light reflected from 3I/Atlas using spectroscopy, they can identify which elements are present on its surface. Early observations have detected signatures of water ice, silicate minerals similar to olivine and pyroxene, and organic compounds containing carbon and nitrogen. That organic material is particularly fascinating. These aren't living organisms, to be clear, but complex molecules that serve as the building blocks for life. Amino acids, the components of proteins, polycyclic aromatic hydrocarbons, ring-shaped carbon structures found throughout the universe, formaldehyde, methanol, and other simple organic molecules. The presence of these compounds tells us about the temperature and chemical conditions in the stellar nursery where 3I/Atlas formed. Dr. Alan Fitzsimmons from Queen's University Belfast leads one of the spectroscopic observation campaigns. His team is using the Very Large Telescope in Chile, one of the most powerful optical telescopes on Earth. He explained their approach. We're essentially doing forensic analysis on a cosmic crime scene. The chemicals present, their ratios, their distribution, all of this tells us about the environment where this object was born. We're reading the biography of another solar system. Beyond chemistry, astronomers are studying 3I/Atlas's physical properties. How fast is it rotating? Initial observations suggest a rotation period of approximately 8.7 hours, meaning it completes one full spin about 3 times per Earth day. That rotation rate tells us about its structural integrity. If it was spinning much faster, centrifugal force would tear it apart. The fact that it's held together suggests it's either a solid chunk or a rubble pile with enough gravitational cohesion to maintain shape. Its brightness varies as it rotates, which indicates an irregular shape. Astronomers are building 3-dimensional models based on these brightness fluctuations. Current estimates suggest 3I/Atlas is roughly cylindrical or ellipsoidal, approximately 1/600 feet long and perhaps 800 feet wide. That's about the size of the Empire State Building lying on its side. But here's where things get really interesting. As 3I/Atlas approaches the Sun, solar heating will warm its surface. If there's ice beneath the dusty exterior, it might start to sublimate, turning directly from solid to gas without passing through a liquid phase. That outgassing could create a coma, a thin atmosphere of gas and dust surrounding the nucleus, and possibly even a tail like a traditional comet. Whether or not this happens will tell us about the object's thermal history. If 3I/Atlas spent billions of years in the frozen depths of interstellar space, its ice might be pristine and volatile, ready to vaporize at the first touch of solar heat. If it passed close to its parent star before being ejected, the surface layers might be depleted of volatiles, leaving only refractory materials that can withstand high temperatures. The James Webb Space Telescope is scheduled to observe 3I/Atlas during its closest approach. Webb's infrared capabilities can detect heat signatures and identify molecules that are invisible to optical telescopes. Its observations could reveal subsurface ice, detect outgassing that's too faint for other instruments, and measure the object's thermal inertia, how quickly it heats up and cools down, which tells us about its internal structure. Radio telescopes are also getting in on the action. The Arecibo Observatory in Puerto Rico. Oh wait, that collapsed in 2020. But the Goldstone Solar System radar in California and the Green Bank Telescope in West Virginia can bounce radio waves off 3I/Atlas if it gets close enough. Radar observations can measure the object's size and shape with incredible precision, down to features just a few feet across. They can also detect rotation rates with far greater accuracy than optical observations. There's even discussion of sending a spacecraft to intercept 3I/Atlas, though the mission timeline would be extraordinarily tight. A fast flyby mission launched in early 2025 could potentially reach the object, snap close-up images, sample its coma if one develops, and maybe even deploy a penetrator to analyze subsurface composition. The European Space Agency has run preliminary trajectory studies. It's technically feasible with existing technology, but it would require approving, funding, and building a spacecraft in a matter of months. That's never been done before for anything beyond Earth orbit. Still, the scientific payoff would be immense. A close-up image of an interstellar object would be worth more than 1,000 distant spectra. We'd see craters, fractures, layering, colour variations, all the geological details that tell the story of an object's formation and evolution. We'd essentially be doing planetary geology on a world from another solar system. And that brings us to perhaps the deepest question of all. Where did 3I/Atlas come from? And what does its journey tell us about the galaxy we inhabit? Tracing 3I/Atlas backward through space is like running a movie in reverse. Watching a bullet fly back to the gun that fired it, astronomers at the European Southern Observatory did exactly this, calculating the object's trajectory through the galaxy for the past 40 million years. The math is staggering. 3I/Atlas has travelled approximately 230 trillion miles since it left its home system. That's 230 followed by 12 zeros. To put it in perspective, light from the nearest star takes 4.2 years to reach us. 3I/Atlas has been travelling for roughly 10,000 times longer than that light journey, crawling through the frozen darkness at a fraction of light speed. During that journey, and it passed through molecular clouds, regions of space where gas and dust congregate before collapsing to form new stars. It drifted past dying red giants shedding their outer layers. It witnessed supernova explosions from a safe distance, shock waves expanding outward at thousands of miles per second. The object you see approaching Earth today has been a silent witness to cosmic events that occurred millions of years before humans existed. But here's the haunting part: we can't identify its parent star. The galaxy rotates like a giant spiral pinwheel, with stars orbiting the galactic centre at different speeds depending on their distance. Over 40 million years. Both 3I/Atlas and its birth star have moved so far from their original positions that tracing the exact connection is nearly impossible. It's like trying to identify which specific tree in a forest dropped a particular leaf after it's blown 1,000 miles in the wind. Dr. Corinne Baylor-Jones from the Max Planck Institute for Astronomy ran simulations attempting to identify candidate parent stars. His team analysed the motion of 7 million stars in the Gaia spacecraft database. looking for any whose paths intersected with 3I/Atlas's backwards trajectory. They found 87 possible candidates, but the uncertainties are enormous. Any of those stars could be the parent, or the real parent might be a faint star we haven't catalogued yet. What we do know is that 3I/Atlas likely formed in the outer regions of another solar system, in a zone similar to our Kuiper belt. This is where icy bodies congregate beyond the orbits of the major planets. In our system, this region contains hundreds of thousands of objects, including Pluto, and it extends from about 30 to 50 times Earth's distance from the Sun. How did 3I/Atlas get ejected? Gravitational interactions with giant planets are the most likely culprit. Imagine a cosmic game of billiards where Jupiter-sized planets scatter smaller objects like cue balls hitting a rack. When an icy body passes close to a massive planet, gravity can either capture it into a new orbit or fling it outward at tremendous speed. If the velocity boost is sufficient, the object reaches escape velocity and leaves the system entirely. Our own solar system does this constantly. Jupiter and Saturn act like cosmic bouncers, ejecting objects from the inner solar system at a rate of several trillion per year. Most of these objects are small, comets and asteroids just a few miles across, but over billions of years, that adds up. The Milky Way galaxy likely contains trillions upon trillions of these rogue objects, drifting through interstellar space with no star to call home. Dr. Amaya Morrow-Martin from the Space Telescope Science Institute studies interstellar populations. Her research suggests something remarkable. There may be more rogue objects wandering between the stars than objects still bound to stars. The galaxy's true population isn't in solar systems, it's in the empty space between them. Think about that for a moment. The stuff of planets, the material that could have become worlds. Most of it might be floating untethered through the cosmic void. 3I/Atlas could have siblings. Thousands of objects ejected from the same system, all travelling in different directions, never to meet again. And here's an even wilder possibility: some of these interstellar wanderers might carry life. Not intelligent life, but microbial life. Bacteria or extremophiles that survive the ejection event and endure the frozen journey through space. This concept is called panspermia, the idea that life can spread between worlds hitching rides on asteroids and comets. We know Earth microbes can survive extreme conditions. In 2020, Japanese scientists revived bacteria that had been dormant in seafloor sediment for 100 million years. Other experiments have shown that bacterial spores can survive vacuum, radiation, and temperatures near absolute zero for extended periods. If microbes from another world were embedded deep inside an object like 3I/Atlas, protected from radiation by layers of rock and ice, could they survive a 40-million-year journey? Dr. Chandra Wickramasinghe, an astrobiologist who has studied panspermia for decades, argues it's not just possible but likely life might not originate independently on every planet. It might spread, riding comets and asteroids across the galaxy. We could all be descendants of microbes that arrived on Earth from somewhere else. Testing this hypothesis is nearly impossible with our current technology. We can analyse the surface chemistry of 3I/Atlas from a distance. But detecting life would require landing on it, drilling into it, and bringing samples back to Earth for analysis. That's not happening with this visitor, but it plants the seed for future missions. The next interstellar object we discover might warrant a dedicated sample return mission. Beyond biology, 3I/Atlas tells us about the efficiency of planet formation. The fact that we're now detecting interstellar objects regularly, 3 in just 8 years, suggests they're common. And if they're common, that means planetary systems routinely eject material. That ejected material represents failed planets, the building blocks that never quite coalesced into worlds. In our solar system, we estimate that for every kilogram of material that ended up in planets, about 1 kilogram was ejected into interstellar space. If that ratio holds across the galaxy, then planet formation is only about 50% efficient. Half the raw material gets thrown away. But that waste material isn't lost. It enriches the interstellar medium, the gas and dust between stars. When new stars form from collapsing molecular clouds, they incorporate material from previous generations. The carbon in your body, the oxygen you breathe, the iron in your blood. All of it was forged in stars that died billions of years ago. Some of that material might have spent time as part of asteroids or comets in other solar systems before ending up here. You are quite literally made of stardust. But you might also be made of pieces of other worlds, fragments that wandered the galaxy before gravity pulled them into the cloud that formed our sun. 3I/Atlas carries this legacy in its composition. The isotope ratios, the mineral structures, the organic molecules, they all preserve a record of processes that occurred in another stellar environment. And by studying those signatures, we're not just learning about one object or one distant system. We're learning about the galaxy as a whole, about how matter cycles through space and time, building worlds, destroying them, and scattering the pieces to build new worlds elsewhere. But there's something more immediate we need to address, a misconception that refuses to die no matter how much scientists explain it. Let's talk about the elephant in the room, gravity. Specifically, the persistent myth that 3I/Atlas could somehow pull on Earth, triggering earthquakes, volcanic eruptions, or tidal catastrophes. This idea spreads like wildfire on social media every time an asteroid makes the news, and it's time to put it to rest with actual numbers. Gravity follows an elegantly simple equation that Isaac Newton figured out in 1687. The force between two objects depends on their masses and the distance between them. Double the mass, you double the force, double the distance, you quarter the force. It's inverse square law, and it's brutally unforgiving when dealing with cosmic distances. Let's calculate the gravitational pull 3I/Atlas will exert on Earth at closest approach. First, we need its mass. Based on size estimates of roughly 1/600 feet long and assumed density similar to cometary material, about 500 kilograms per cubic meter, 3I/Atlas. Likely masses around 200 million metric tons. That sounds enormous until you compare it to Earth's mass of 6 trillion kilograms. Earth outweighs 3I/Atlas by a factor of 30 quadrillion. At the closest approach distance of 26.4 million miles, or 42.5 million kilometers, the gravitational force 3I/Atlas exerts on Earth is approximately 0.0000000000003 newtons. For reference, a single mosquito landing on your arm exerts about 0.0000001 newtons of force. 3I/Atlas's gravitational tug on our entire planet is 1/millionth the force of a mosquito. But people worry about tides. After all, the moon causes tides. Right, can't 3I/Atlas do the same? Let's compare. The moon mass is 73 quintillion kilograms and orbits at an average distance of 238,000 miles. At closest approach, 3I/Atlas will be 110 times farther away than the moon and 1 trillion times less massive. The moon's tidal force on Earth is about 10 million trillion times stronger than anything 3I/Atlas could produce. Dr. Eric Asfalg, a planetary scientist at the University of Arizona, addressed this directly in a public lecture. Worrying about 3I/Atlas triggering earthquakes is like worrying that a butterfly flapping its wings in Australia could knock over your house in New York. The forces involved aren't just small, they're incomprehensibly negligible. But the myth persists because humans struggle with scale. We evolved to understand forces we can feel the weight of a rock, the pull of a rope, the impact of a punch. We didn't evolve to intuitively grasp the difference between millions and quadrillions. Our brains compress these numbers into a vague sense of very big, which makes it hard to appreciate just how utterly insignificant 3I/Atlas's gravity is compared to Earth's own mass. Here's another way to think about it. Every time a large cruise ship sails past a coastline, it exerts more gravitational pull on that coastline than 3I/Atlas will exert on the entire planet. Yet coastlines don't crack and crumble when cruise ships pass. Buildings don't collapse. Earthquakes don't trigger. The forces are simply too small to matter. What about electromagnetic effects? Some conspiracy theories claim that charged asteroids could interact with Earth's magnetic field, causing auroras, power grid failures, or atmospheric disturbances. This one has a tiny kernel of truth wrapped in layers of nonsense. Yes, asteroids can be electrically charged. Solar wind, the stream of charged particles from the sun, can build up static electricity on an asteroid's surface, similar to how you build up charge shuffling across carpet in winter. But the voltages involved are minuscule, and the object's charge dissipates quickly when it enters a planet's magnetic field environment. Dr. Mihaly Horani at the University of Colorado studies asteroid charging. His research shows that even large asteroids carry charges equivalent to a few hundred volts distributed across their surface. That's about the same as touching a doorknob after walking on carpet. It produces a tiny spark. Nothing more. There's zero possibility of this affecting Earth's magnetic field, which is generated by a dynamo of molten iron 1/800 miles beneath your feet. Then there's the radiation scare. Could 3I/Atlas emit dangerous radiation after all? It's been travelling through deep space for millions of years, exposed to cosmic rays and interstellar radiation. Couldn't it be radioactive? Space doesn't work that way. Cosmic rays are high-energy particles that bombard objects in space, but they don't make those objects radioactive in any meaningful sense. An asteroid can't absorb radiation and then re-emit it like some kind of cosmic battery. Yes, cosmic ray impacts can produce trace amounts of radioactive isotopes in surface materials, but the quantities are infinitesimal and confined to the object's surface. You receive more radiation exposure from a cross-country flight, about 0.035 millisieverts, than you would from standing directly on 3I/Atlas's surface for a year. The inverse square law applies to radiation just as it does to gravity. At 26 million miles, any radiation from 3I/Atlas is diluted to absolute insignificance. What's fascinating is why these myths persist despite scientific evidence. Psychologists who study risk perception have found that unfamiliar threats feel more dangerous than familiar ones. You drive a car without anxiety even though car accidents kill over 40,000 Americans annually. But an interstellar asteroid, that's exotic, unknown, and therefore frightening even though the actual risk is zero. Dr. Paul Slovic, a psychologist at the University of Oregon, explains it as the dread factor. Events that are catastrophic, uncontrollable. An unfamiliar trigger stronger fear responses than events that are statistically more dangerous but familiar. Asteroids hit the dread factor trifecta. They come from space. We can't control them, and most people don't understand orbital mechanics. Media coverage amplifies this. A headline reading "Interstellar object makes close approach" sounds ominous. The same headline reading "Distant space rock passes harmlessly 26 million miles away" doesn't generate clicks. News organizations know that fear drives engagement, so they frame stories to maximize anxiety even when the science says there's nothing to fear. Social media makes it worse. Algorithms prioritize content that generates strong emotional reactions. A sober, accurate explanation of orbital mechanics gets ignored. A sensational claim about impending disaster spreads like wildfire. Within hours, You have thousands of people sharing misinformation, each share reinforcing the false narrative. But here's the thing, you now have the tools to counter this. You understand inverse square law. You can calculate gravitational forces. You know that distance matters enormously and that 26 million miles is a comfortable buffer. When someone shares a panic-inducing post about 3i/Atlas, you can respond with facts, with numbers, with the calm confidence that comes from understanding the physics. Science isn't about blind faith in authority. It's about verifiable calculations, repeatable observations, and logical conclusions drawn from evidence. Everything astronomers say about 3i/Atlas being safe can be checked, verified, and confirmed by anyone with basic math skills and access to the data. That's the beauty of science. It's transparent, testable, and it works regardless of whether you believe in it. So when March 14th arrives and 3i/Atlas makes its closest pass, you can watch with fascination instead of fear. You can appreciate the extraordinary cosmic coincidence of an interstellar visitor gracing our neighborhood. You can marvel at humanity's ability to track, predict, and understand these wanderers. And while the rest of the world panics over nothing, you'll understand exactly why we're safe and what we're gaining from this incredible encounter. Beyond the safety calculations and the scientific data, 3i/Atlas represents something profound proof that we live in a galaxy teeming with wanderers, and we're only just beginning to detect them. Before 2017, interstellar objects were purely theoretical. Astronomers knew they should exist based on models of planetary system formation, but nobody had actually seen one. Then Oumuamua appeared, and suddenly the theoretical became real. 2 years later, Borisov confirmed it wasn't a fluke. Now, with 3i/Atlas, we're establishing a pattern. Interstellar visitors aren't rare anomalies. They're regular occurrences we simply lack the technology to detect. Dr. Avi Loeb from Harvard University has studied interstellar object populations extensively. His research suggests something staggering. At any given moment, there are roughly 10,000 interstellar objects passing through our solar system. Most are small, just a few feet across, invisible to our telescopes. But they're there, silently crossing our neighborhood like commuters passing through a train station. 10,000 objects, right now, drifting through the space between planets, following hyperbolic trajectories, carrying material from other stars. Some passed closer to Earth than the Moon, and we never knew. They came and went in darkness, undetected and unrecorded. But our detection capabilities are improving exponentially. The Vera C. Rubin Observatory, set to begin operations in 2025, will survey the entire visible sky every 3 nights using a camera with 2 billion pixels. That's over 200 times more pixels than the Pan-STARRS telescope that's been discovering most near-Earth objects for the past decade. Rubin Observatory's sensitivity means it will detect objects 100 times fainter than current surveys can see. What does that mean for interstellar object discovery? Conservative estimates suggest Rubin Observatory will detect 1 interstellar object per month. That's 12 per year, compared to the 3 total we've found in 8 years. Within a decade, we'll have catalogued over 100 interstellar visitors, each one a data point revealing the composition, structure, and demographics of objects wandering between the stars. Dr. Meg Schwamm, a planetary scientist at Queen's University Belfast, captured the significance. We're about to go from knowing almost nothing about interstellar populations to having statistical samples. We'll be able to answer questions we couldn't even ask before. What's the average composition? What size distribution dominates? Are rocky objects more common than icy ones? Do certain types come from specific stellar environments? This matters because interstellar objects are fossil records of planetary system formation. When a star forms, it's surrounded by a disk of gas and dust. that disk clumps together, forming asteroids, comets, and eventually planets. But not everything gets incorporated into planets. The leftovers, the building blocks that didn't quite make it, get scattered. Some stay in the outer reaches of the system, some get ejected entirely. By studying the chemistry and structure of interstellar objects, we're essentially conducting archaeological digs of other solar systems. We're learning what materials were present when those systems formed, what temperatures and pressures dominated during planet formation, what processes were universal and which were unique. Consider the implications for the search for life. If we find organic molecules are common in interstellar objects, that suggests organic chemistry is widespread throughout the galaxy. If we find amino acids, the building blocks of proteins, that strengthens the case that life's chemical precursors are universal. If, and this is a big if, we ever detect biosignatures, actual evidence of life in an interstellar sample, that would revolutionize our understanding of biology's place in the cosmos. Even without finding life, the data matters. NASA's Dragonfly mission, scheduled to launch in 2027, will explore Titan, Saturn's largest moon. Titan has lakes of liquid methane, organic molecules raining from the sky, and chemistry that might parallel early Earth. But how do we know if Titan's organic chemistry is typical or exceptional? By comparing it to the organic inventory in interstellar objects. If 3i/Atlas and future visitors show similar organic compounds, that suggests these molecules form readily under a wide range of conditions. The same logic applies to the search for exoplanets. We've discovered over 5000 planets around other stars, but we can only observe them indirectly. We see the dimming when a planet crosses in front of its star. We measure the wobble in the star's motion caused by the planet's gravity. We analyse starlight filtered through the planet's atmosphere, but we can't collect samples, we can't land probes, we can't directly touch the material of another solar system. Except we can. Every interstellar object is a sample return mission we didn't have to launch. It's physical material from another stellar environment delivered to our doorstep for free. If we can intercept one, land on it, drill into it, and bring pieces back to Earth, we'd have fragments of another world to study in laboratories with instruments far more sophisticated than anything we could fit on a spacecraft. Japan's Hayabusa 2 mission demonstrated this is possible. It rendezvoused with asteroid Ryugu, collected samples, and returned them to Earth in 2020. The total mission cost about $270 million. Analysing those samples revealed organic molecules, water-bearing minerals, and details about solar system formation that reshaped our understanding of planetary origins. Now imagine doing that with an interstellar object. The scientific return would be extraordinary. We'd learn about stellar environments light years away without ever leaving our solar system. We'd compare alien chemistry to our own, identifying what's universal and what's local. We'd trace isotope ratios back to specific types of stars, potentially identifying the parent star's mass, age, and composition. Some scientists are already planning for this. The European Space Agency's Comet Interceptor mission, scheduled for launch in 2029, is designed to wait in space until a suitable target appears, either a pristine comet from the Oort cloud or, if opportunity allows, an interstellar visitor. The spacecraft will split into 3 modules that simultaneously image the target from multiple angles, sample its coma, and analyse its composition. If an interstellar object passes through during the mission's operational lifetime, Comet Interceptor could provide our first close-up look. But here's the beautiful part: you don't need a space mission to contribute to this science. Amateur astronomers have already played crucial roles in tracking interstellar objects. When Comet Borisov was discovered, amateur observers worldwide contributed light curve measurements, rotation period estimates, and colour photometry, Their data, combined with professional observations, created a more complete picture than either group could achieve alone. With 3 Ice/Atlas, amateur astronomers with telescopes as small as 8 inches in diameter will be able to observe it during closest approach. You could track its position, measure its brightness, document any outgassing activity, and submit your observations to the Minor Planet Center. Your measurements, combined with thousands of others, contribute to the orbital refinement and characterization efforts. There's even a NASA program called Target Asteroids that trains citizen scientists to observe near-Earth objects and interstellar visitors. You don't need a PhD, you just need a telescope, a camera, and the willingness to learn. The program provides tutorials, software tools, and mentorship from professional astronomers. This is science operating at its best, transparent, collaborative, and accessible. The barriers between professional and amateur are dissolving. The data is open, the tools are available, the opportunity is real. And as detection technology improves, as surveys become more sensitive, as spacecraft missions target interstellar visitors, we're entering an era where these cosmic wanderers transition from mysterious anomalies to routine subjects of study. Which brings us to the question that's been hovering at the edge of this entire discussion. What does all of this mean for humanity's place in the universe? Stand outside tonight and look up at the stars. Every point of light you see represents a solar system, potentially with its own planets, its own asteroid belts, its own comets. And around each of those stars, gravitational dynamics are playing out, scattering material into interstellar space just as our solar system does. We're not isolated. We're part of a galactic ecosystem where matter constantly circulates between stellar systems. Objects leave, objects arrive, and in that exchange, information travels across distances that would take human spacecraft millions of years to cross. 3 Ice/Atlas is proof of this exchange. It spent 40 million years travelling from another star to ours, carrying a message we're only now learning to read. But it's not delivering this message to us specifically. Earth just happens to be here at this particular moment in cosmic time. If our planet had formed 1 billion years earlier or later, we'd never see 3 Ice/Atlas. If we were located in a different spiral arm of the galaxy, it would pass through someone else's neighbourhood, assuming anyone is there to observe it. This raises a profound question: how many other civilizations have watched interstellar objects pass through their systems? Are there astronomers on distant worlds right now tracking wanderers from our solar system? Objects ejected by Jupiter billions of years ago that have since travelled across the galaxy, Dr. Greg Laughlin, an astrophysicist at Yale University, calculated the odds. His team estimated that over the past 5 billion years since our solar system formed, we've ejected approximately 100 trillion objects into interstellar space. Most are small, cometary nuclei and asteroid fragments, but some are likely planet-sized. Rogue worlds kicked out during the chaotic early days of planetary formation. Those 100 trillion objects are now scattered throughout the Milky Way. Some have passed through other stellar systems, some have been captured into orbit around other stars. A few might have collided with planets, delivering material from our solar system to alien worlds, in a very real sense. Earth has left its fingerprints across the galaxy, and we're receiving fingerprints in return. 3 Ice/Atlas carries isotope ratios that reflect conditions in its birth environment. When it formed, its parent star's radiation environment, its distance from that star, the composition of surrounding gas and dust. All of these factors influence the chemical makeup we're detecting today. By measuring those signatures, we're indirectly observing a stellar environment we'll never visit. This has implications for the Drake equation, the famous formula astronomers use to estimate the number of communicative civilizations in our galaxy. One of the equation's terms is the number of habitable planets, but how do we define habitable traditionally? We think of the habitable zone as the region around a star where liquid water can exist on a planet's surface. Too close, water boils; too far, it freezes. But interstellar objects complicate this picture. If panspermia is real, if life can survive on wandering asteroids and comets, then habitability isn't tied to a star's warmth. A subsurface ocean on an interstellar object, heated by radioactive decay rather than starlight, could potentially harbour life in the frozen darkness between stars. Life wouldn't need planets. It could exist in the void itself. Europa, Jupiter's ice-covered moon, might be our best local analogy. Beneath a shell of ice up to 15 miles thick lies an ocean containing twice as much water as all of Earth's oceans combined. That ocean isn't heated by the sun, it's heated by tidal flexing from Jupiter's gravity and residual radioactive decay in Europa's rocky core. If life exists in Europa's ocean, it proves life doesn't need sunlight, just liquid water and energy. Now imagine an interstellar object with similar characteristics. A wandering ice world, ejected from its birth system, travelling through the galaxy with a subsurface ocean kept liquid by internal heat. Could microbial life survive in such an environment for millions or billions of years? We don't know, but we can't rule it out. Dr. Claudia Alexander, a planetary scientist who studied comets before her death in 2015, once said something that stuck with me. Every comet is a time capsule from the birth of the solar system, but interstellar comets are time capsules from other solar systems. They're letters from distant pasts, written in languages we're only beginning to understand. Reading those letters requires humility. We've been studying astronomy seriously for maybe 400 years since Galileo first pointed a telescope at the sky. Modern astrophysics is barely a century old, and yet we're already decoding messages from objects that began their journeys when our most distant ancestors were still learning to walk upright. The pace of discovery is accelerating. In 2017, Oumuamua was a surprise. In 2019, Borisov was confirmation. In 2024, 3I/Atlas is becoming routine. By 2030, we'll likely be tracking dozens of interstellar objects simultaneously, comparing their compositions, mapping their origins, and building a statistical understanding of what's out there between the stars. This knowledge serves a practical purpose beyond pure curiosity. Understanding the interstellar object population helps us assess long-term collision risks. While 3I/Atlas poses no danger, future visitors might not be so benign. An object on a direct collision course, detected decades in advance, gives us time to mount a deflection mission. But we can only deflect what we detect, and we can only detect what we're looking for. The asteroid survey programs, the detection networks, the international coordination, all of this infrastructure exists because we learned the hard way that threats from space are real. The Chicxulub impact 66 million years ago killed the dinosaurs. The Tunguska event flattened a forest. Chelyabinsk injured over 1,000 people. These weren't mythological events or Hollywood fiction. They were real disasters caused by objects from space. But here's the hopeful part: we're the first generation in human history with the technology to see these threats coming and the capability to do something about them. Our ancestors watched helplessly as comets appeared in the sky, interpreting them as omens of doom because they had no understanding of orbital mechanics. We watch the same phenomena with telescopes, calculate trajectories, and know with certainty whether we're safe or not. That knowledge is power. It transforms existential anxiety into manageable risk. It replaces superstition with mathematics. It gives us agency in a universe that often feels indifferent to human concerns. So when 3I/Atlas makes its closest approach on March 14th, 2025, it won't be an omen or a threat. It will be a cosmic milestone, a visitor from another star reminding us that we live in a dynamic, interconnected galaxy where matter and perhaps life itself travels between worlds. You'll be able to see it if you have access to a decent telescope. It won't be a spectacular naked eye display like a bright comet. It'll just be a faint dot moving slowly against the background stars. But knowing what that dot represents, where it came from, how long it travelled, and what it carries, that transforms it into something extraordinary. Because 3I/Atlas isn't just a space rock. It's proof that we're part of something vast, something ancient, something that connects stars across the galaxy in ways we're only beginning to understand. And the fact that we can observe it, track it, study it, and learn from it, that's a testament to human curiosity, ingenuity, and our relentless drive to understand the universe we inhabit. The visitor will pass. It will leave our solar system and continue its journey through the galaxy, perhaps to be discovered billions of years from now by astronomers orbiting a star we can't even see from Earth. But the knowledge it leaves behind, the data we collect, the questions it answers and the new ones it raises, those will remain. And they'll prepare us for the next visitor, and the one after that, and all the cosmic wanderers yet to come.